Welcome to this presentation on IoT security concerns and Renesas Synergy solutions. My name's Haydn Povey, and I've been working very closely with Renesas to explore and to expose the security capabilities of the Synergy platform for the last 12 months or so. So a little bit about me, we'll move through this quite quick. So I founded Secure Things about 18 months ago. We're a security consultancy. So we're working with a lot of different companies around auditing their security requirements, building security architectures, helping them enforce those. And we do that from a silicon level, RTL, all the way up to a system and meta system level. With Secure Things, we've this week talked a little bit about Secure Deploy out on the show floor there, and Secure Thinking is the name of our consultancy services. So why listen to me? Why am I up here? What do I know? Well, for the last 5 years, I was the director of all security technologies at Arm. So I ran everything from Arm's secure core, tamper-resistant products, which go into smart cards, SIMs, secure elements of various types, all the way up to the Trust Zone security platform, which goes into the majority of cell phones, tablets, servers, and all of those types of platforms. And of course, at Arm, that was dealing with both the engineering of the security into the RTL and into the silicon, but also working through the design chain there with OEMs, ODMs, MNOs, and all the other TLAs that you can imagine. Previous to that, so I did that for the last 5 or 6 years. Previous to that, I was director of embedded processors. So the Cortex M3, M4, M0, all of those are my babies. So I was the original product manager, product director for the Cortex M3, the first of those ARM processors, which from inception to domination. So here we are, and Renesas has finally brought through a Cortex M processor. So I've apologized many times for that. Okay. And before that, again, I was with National Instruments for 10 years in Texas and also in the UK. So I've done a lot of work with real-time systems. So understanding the needs of deterministic systems, very hard real-time systems, and what happens when something goes wrong and it goes bang. So enough about me. So obviously in this one we're looking at Synergy and the security, but we obviously have to look at that from a holistic perspective. The devices themselves, the platform and how this fits into the software, the SSP, and the solutions that we're trying to achieve. And I think with security especially, it's this last one which is the really hard one. Because security is something that you have to think around systemically. You have to understand what you're trying to achieve before you start designing the system. It's not something that you can easily graft on afterwards, or at least not for a graceful or, in many cases, useful system. So what I want to do in this presentation is look at the requirements in a more holistic view than perhaps you've seen before, and then map those over to the technology that we have in Synergy and explore how we can use those to build better systems. So in terms of the agenda, we're under attack. We know that, we've seen the press. We want to look at how we build protection with Synergy, how we ensure integrity, how we enable confidentiality and privacy, how we safeguard availability, and we look at how we manage devices over their entire life cycle, and then summary and Q&A. So I probably don't need to tell you this. You're all in this room. You understand we're under attack. There's a bunch of really bad guys out there. And in most cases, they're the smartest guys in the room. They have practically infinite resources. They're very smart. There's a lot of them. Many of them have nation states stood behind them. And they only have to get it right once. We have to get it right all of the time if we're going to manage systems. So let's put that in numbers. You know, how secure is your system? Is it 80% secure? Is it 90? Is it 99% secure? 99.9? 99.99? They only need that 0.01 time to break your system. And your entire investment in R&D, millions of dollars, is lost. So how do we manage that? Well, we have to develop systems where we expect to be compromised in some ways. We have to think about how we manage that over the long term. So we have billions of devices, trillions of connectivity providing this huge attack surface. We have to interwork with other manufacturers, other vendors. The nature of the IoT is it's not all going to be one guy's stuff anymore. So how do we close that attack surface? The nature of IoT, again, these billions of devices, there's no one size fits all. The security that we need on a light bulb is very different from the security that we need on a car. But the same principles do apply, and we have to apply those. The other problem with all of this is there's real money here. There is real money for the cyber criminals. There is real money for cyber warfare and all these sort of things. So we're starting to see ransomware being developed for IoT systems. I know that this came out in some of the panel discussions on Monday. You know, who wants to attack a light bulb? Who wants to attack a fridge? Well, if those things are inside your trusted network, that is how you exfiltrate the data from your PC. We have seen real-world attacks where people have launched attacks on light bulbs, connected light bulbs, to bounce attacks directly onto PCs to get people's bank details. You are only as strong as the weakest link in the chain. And if that's your product that brings down a larger system, you've got a problem. So the other problem with IoT as opposed to traditional InfoSec, information security, is that the consequences of an IoT attack far outweigh those of InfoSec. With InfoSec, you can steal people's names, address, bank details. There's big back-end systems protecting most of us from that. The reality with IoT attacks, though, is that they are both far more real and they're far more immediate. They're far more real because you're switching off my heating and you're switching it off today in the middle of winter. That's a big problem, whereas somebody stealing my ID is a relatively abstract problem. So we have to think about security at a deeper level and far harder with IoT than we've ever had to with InfoSec. And look what a mess they've made of that. So we need to think about these different things. We need to think about, you know, the failure of industrial systems, people capturing and disrupting attacks to gain control of intelligence. We have to think about how they manipulate data. Again, you know, with the transportation system, if somebody can manipulate what's going on in the system, they can change the flow of traffic, they can cause chaos. And we've been dealing with one customer where they're really scared about data being altered in their system, so they're producing too much energy and they're having to dump it. And over time, they'll spend more and more money producing energy that nobody wants. And that's a big risk for them. It's an economic risk. And then, of course, privacy and confidentiality on these things pose, you know, critical risks to safety, security, and privacy. So we probably know that, but it's worthwhile going through it. Here's a scary number, $1 trillion. That's the estimated cost of an attack on the smart grid. Again, those people who are aware of this will know that when the NSA did the full audit of the grid at the moment, they found it full of remote access Trojans and other malware. Those risks are real, they're out there. It's really expensive. So how do we start to put this right? Well, we're a bit late, frankly. So I deal with, again, some of the UK agencies, some people in the secret intelligence service in the UK have called the IoT a slow motion train wreck. Because we know it's going wrong, We can see the accident coming down the tracks, nothing we can do about it. Well, we can, and we have to start today. What we have to do is develop a set of capabilities. And again, many people, if you're aware of securities, these are fairly well-known terms, but there's a lot of people where this is new. We have to develop a strong root of trust, a very strong integrity in that system where we can prove cryptographically that our device is safe. And of course, we have to ensure that we can manage our devices over their entire life cycle. So we're going to have to create trust. We're going to have to manage trusted relationships over the full lifetime of the device. And at the end, we're going to have to destroy trust as well, when we throw an item away or when we pass it on to somebody else. Now, a lot of people take confidentiality and privacy and they confuse it with cryptography. Cryptography is important. It's a really important underpinning technology to all three of these. But cryptography is only a technology. It's only as good as its implementation, and it's only, in most cases, people think of it as protecting data in flight and at rest. But security has a lot of other capabilities. We have to protect intellectual property. If you've been out on the show floor the last couple of days, you may have seen our demo where we were doing secure manufacturing. So we can protect intellectual property from when it's generated to when it's delivered into the chip. As I say, confidentiality of data, the need to create robust foundations, the need to separate critical functions so we have availability. So when we are compromised, and we will be, everybody will be, you can still maintain some capability in the system. And then how do we update? How do we remediate? How do we fix what's gone wrong? So again, this comes back down to integrity, availability, and confidentiality. And let's start linking those back to Synergy. So in terms of Synergy, we have an integrated solution for higher security. So what Renesas have done and what we've been working with Renesas around is how we bring these technologies out as capabilities which are really useful and make a difference. A couple of the nice things. So with confidentiality, we're looking to increase protection of data at rest and in flight. With Synergy, we're developing these security capabilities across the portfolio. So from the lowly S1 to the powerful S7, they all have the ability to do fast, symmetric cryptography. They all have the AES stream ciphers and other cryptography accelerators. So these are in here. Some of the asymmetric cryptos are in the S5 and the S7, and in the next presentation we'll go into more details around that. The other nice thing about confidentiality is because we're using these accelerators, which we'll talk about later on, with standard APIs we can reduce our code base. One of the challenges I've always found when working with people around security is they go, yeah, but I don't understand the math. How does AES work? Very few people do. Yeah, very few people understand permutation boxes and S boxes and various other things. You don't need to. All you need to do as engineers is call through some standard APIs, register the key length that you want to use, put in the message, and hopefully it should work. And that's where we need to move to with security. It needs to be commonplace, it needs to be everywhere. From a confidentiality perspective, because we're using a set of crypto engines, and these are constrained in the Synergy crypto engine, we can tightly integrate that as a separate block. And inside there, we can protect our secrets and we can prevent data leakage out of that SCE as well. In terms of the integrity, we can deliver a new level of trust and trustworthiness in our product. We've developed an integrated root of trust. Again, the demo that we had on the show floor the last couple of days demonstrated a secure boot. So a secure kernel which had a secure boot in it, the seeds, to develop that root of trust. Now that enables us to have this constrained and measurable boot process. Doesn't take a lot of space, doesn't take a lot of performance. What it does do is it guarantees that root for the device. And that's useful, again, in manufacturing security and in application security as well. And the nice thing of the integrity, and we'll have a look at how we do this using the secure MPU, it also allows us to isolate sections of code. Now, Synergy is a microcontroller, it's not a microprocessor. It doesn't have a memory management unit, but it does have 4 memory protection units. So that includes the standard ARM MPU, MPUs for bus masters and bus slaves, and then a new technology which is called the secure MPU. And this secure MPU is a key component in enabling us to build a high integrity system. And then availability, and again, these are all tightly related. This allows for security across the life cycle. It allows critical systems to be promoted, critical systems to be isolated to promote uptime. It enables ongoing monitoring and management of functionality before an attack, during an attack, even and after an attack, and a platform for updates. Why is this important? Well, with our mobile phones, we're used to high security on our mobile phones, and we swap those out every 2 years, perhaps every 3 years. With our PCs, we perhaps swap them out every 4 or 5 years. How often do you swap out your HVAC system or your furnace? Once every 20 years? How often do you swap out your white goods? Once every 10 years? How often are we going to find errors in the code in those devices? A lot more often than that. So what we have to do is develop platforms for managing life cycles and remote updates. And this is just a reality of the Internet of Things. So how do we start doing this? Let's kind of go to the next level. So a nice old castle here. So confidentiality is reliant on a high integrity platform. If you pardon my French, crap in, crap out. If you do not trust the unit where the data is coming from, it doesn't matter how good your encryption is, it can still be wrong. So how do we measure whether that data is correct? And how do we make decisions based on that as well? So big data is only as good as the data that we get in, and if that's wrong, the whole premise of big data falls apart. So traditionally, embedded systems, we all know these were islands. It's not the case anymore. We're now highly connected with very complex system definition. So how do we develop integrity? As I say, we have to do this through a root of trust. A nice little graphic here of the roots shaking hands. So what we need to have for our root of trust is out of reset, we need to go into a very known constrained state which we can crawl all over from a code perspective, and cryptographically we can prove is correct. So what we can do with that is use our hardware configuration to do secure memory partitioning, and we can set up some robust defenses prior to secure boot execution. Again, I hate to point back to the show the last couple of days, but we were showing the secure boot, which demonstrated all of these features. So at the bottom we have some cryptographic identifiers. These are based on the true random number generator, which is the latest NIST 8900 standard. It is a very, very good random number generator. People tend to forget that you have to have the basics right. If you don't have a high enough entropy source in the device, you will never generate seeds with enough difference in them, and therefore the devices will be open to be broken. Good security always starts with high entropy. And in Synergy we have this really good random number generator there. And this allows us to create a seed, for example, 512-bit, and then do key derivation and storage of those keys. Why is that important? Well, because the unique identifier on a normal chip is not sufficiently different. If they all come from the same wafer, their unique IDs are all inside 10,000 of each other. It'd take you half a day to break that, if not less. So we have to get the cryptographic identifiers right. We have to secure the hardware configuration. And with Synergy, this means ensuring that your secure MPU is set up correctly, and also the flash access window, and potentially switching off the JTAG. So we have secured JTAG as part of the Synergy platform. Once we have those components, we can do the secure boot, we can execute through that, we can set up all of our private keys, and once we're happy, once we can make an attestation, a measurement of our platform, then we can launch our trusted software, our RTOS or other trusted software, and then and only then can we trust our data. And without trustworthy data, we may as well all give up and go home. Okay. So this is a simple diagram of, again, what we were showing out on the floor. And here, for example, we're taking the Synergy devices and we've done some initial personalization. And what we're moving towards with Renesas is that that personalization and the injection of the secure kernel happens at the fab. So at the birth of the device, we're injecting the keys and all the key material to make that device cryptographically unique. So this is a very strong key set which can't be replicated, can't be guessed. We keep the private key inside the device, and we share the public key through a device certificate. And that device certificate is signed by Renesas. We can verify if we want with the OEM which devices, so it can be just, hey, any Synergy device, or it's got to be a specific type of device, or it's got to be a specific set of identifiers. We can manage that, it's relatively simple. And then we can get these into the contract manufacturer, we can bring together the code, we can ensure that only the right number of devices are produced, we can ensure that the code is never exposed. Again, in the example, we showed that we encrypted the code at the OEM, and we only decrypted it in place on the chip. So everything going into the chip was encrypted, the software image and all the key material were encrypted using asymmetric encryption, and they were only decrypted in place on the right chips. And then we can go and delegate ownership to our end user. Delegation of ownership is a massive subject. If you ever want to read a very long essay on it, talk to any of the mobile phone guys and they'll tell you what a pain delegation of ownership is, but it's an important aspect. So how do we enable confidentiality? Well, as I say, confidentiality and cryptography are often mistaken. Cryptography is an important part of confidentiality, but it's not the only aspect of it. So confidentiality is critical to managing privacy of data. We won't get into the aspects of privacy in this conversation. You know, there's a lot of different viewpoints on who owns data and how private it should be, but that's fine. But we have to trust our data if we're going to operate it in a big data system. Confidentiality is important, but it is, and passing messages is critically important, but it is only the tip of the iceberg of the cryptographic setup that you have to go to make that message happen. We have to generate public-private keys. Now we can do that, as I say, on the manufacturing line. We have to manage ways of exchanging keys securely. We then may need to cryptographically wrap and store some of those keys. So this is all setting up the channel. We'll then create a symmetric key for the data that we want to pass. We have to encrypt that symmetric key with an asymmetric key before we send it. We have to share it. Perhaps at the far end, we need to wrap and store that key because we can't store keys out in the open because that's how systems get broken. And once we have a protected channel and once we have shared the symmetric key, then we can pass some data. So as I say, confidentiality is more than the fact that, hey, I'm going to do some encryption. We have to think about how we want to share data and where we want to share data. So what components do we have in here? I've kind of mentioned some of these. First of all, we have the TRNG. So this is a very high entropy source. It meets all of the latest specifications, and there's a new one coming out which we think will meet as well, but that's not available yet in terms of a spec. We have a bunch of hash accelerators in there as well. So if we need to do hash functions, so we're looking at confirming the packaging of code or of a data packet, then we have the hash acceleration in there. We have a symmetric crypto accelerator, so this is obviously all of the AES modes, and I'll talk more about this in the later session, but the AES here is very advanced, so it's not just AES 128, we also cover 196 and 256. And we cover all of the standard modes. If you look at other vendors out there, some of them have some AES engines, but they don't go beyond CBC. The engine that we have in Synergy covers the vast majority of the different ciphers that you will find with AES. Cover triple DES as well as a number of the stream ciphers, RC4 and others. My personal preference is, unless it's for a legacy reason, I would never touch triple DES. It's officially broken. So, but from a legacy perspective, we may need to still connect some devices. So the nice thing about having these accelerators is they allow for that very rapid encryption or decryption of messages. It reduces power. It also reduces complexity because the API that we have to those with Synergy is a lot easier than having to write your own code, and believe me, we've been doing a lot of that recently. And then in terms of the asymmetric crypto acceleration, so this is a piece of hardware, and this includes some primitives for both ECC and RSA. Now, this in a microcontroller is a huge leap forward. So some other microcontrollers allow for symmetric AES encryption, but to my knowledge, there are no other ones out there which have asymmetric cryptography acceleration. And this is really important because as we move from today's system to more complex systems, we are going to be setting up more asymmetric pairs. In the past, you would install something and you would set up the ECC once, twice. You authenticate it once or twice. In the future, I don't think that's going to be the case anymore. We're going to have to pair more and more devices as we go to multi-vendor systems, zero trust models. We have to presume that we don't trust anything else, and therefore I have to create a secured tunnel to all of these other devices. I don't trust you, I'm going to validate your information. And of course, asymmetric encryption is the key way of doing that. Of course, inside here, there are some other things. There is a unique ID. It's not the cryptographic one, but it's still a large unique ID. We have secure key storage, which is included in the engine here, and some readout protection as well. And we sandwich that between this certifiable root of trust and a software security library with the APIs built into that. So again, why? Well, because the reality is that we are transitioning from monolithic solutions to these multi-vendor systems and solutions with many, many different components in there. Authentication, authorization, and trust are going to become critical issues in those systems. How do I authenticate devices into a network? How do I authorize those? So authorization is often overlooked. It kind of seems the same as authentication, but in a hospital scenario, the janitor shouldn't be able to reset the insulin pump. Yeah, that's the doctors or the nurses. So you have to ensure that you can do authorization as well as authentication. And trust and trustworthiness are important in there. And Synergy, enables that. And we do hit the NSA Suite B level of encryption across the platform here. And this is kind of the high watermark. So this is where, for many years, we were trying to get with mobile phones. As I said earlier, the IoT security is more important than your mobile phone security because there's a far higher likelihood of something going bang. So, the last of the three, integrity, confidentiality, availability. How do we start dealing with this? Well, as I say, cyber attack is not an if, it's a when. If you don't believe that your device is going to be attacked, you're living in a dream world. It will be attacked. They will find issues. They will find attacks. At some point, you'll probably be owned. No matter how good your security is, we're all human. We all make mistakes. We all forget to limit the variables. We all forget to limit the ports. We all forget to limit the debug. Stuff happens. We'll get better over time, but then the next generation comes through and that has the same issues. So we do see attacks growing. We see the value of attacks growing. We see the number of systems exploding. Perhaps the wrong term there, but there's a lot of wins in there. We presume that something in the trusted network is compromised. Again, this can be your connected light bulb. That's the weakest link in the chain. So we have to have security pervasive throughout our network. My personal belief is I think that security belongs everywhere. If anything is connected, if it has a CAN bus on it, if it has an Ethernet port on it, if it has Wi-Fi on it, if it has any radio on it, it needs to be secured because otherwise people are going to attack that node. Some of the attacks may be silent for a very long time. And blacklisting of known compromises is not sufficient on its own. You can't say, well, I know what a bad attack looks like because these things are coming out at a rate of knots. So availability requires isolation of system components, isolation of the flaws, and also simplifying of our components so we can properly test and manage each of those components. So I was talking to somebody the other day, and a lot of security is the ability to do pen testing. Awareness of communication, cryptographic measurements of the status, and then very importantly, recovery and remediation. So again, if we make the assumption that we're going to be owned at some point, we have to find a mechanism to isolate the flaw, download an update, make a new package, get rid of the bit which was bad, and update and manage that system over the full life cycle. And again, that can be 20 years. We know with Heartbleed and others, we have a problem with SSL. We have a problem probably with every piece of software that we use. We just don't know it yet. So how do we do that? Well, again, this is where the secure MPU and the flash access window capabilities of Synergy sets it apart. We can use this to create a separate sanctuary where we can have our secure boot, or we can have other critical components of software which are managing the system. This allows us, if something goes wrong in user mode or in supervisor mode, it enables us to identify that something's gone wrong, and it allows us to recover and remediate. So traditionally, ARM-based microcontrollers, they have user mode and supervisor mode, and Some RTOSs are built to use supervisor mode, but rarely do in practice. Isolation on microcontrollers, again, in my knowledge, traditionally is pretty bad. Very few people really use the MPUs as they were intended. So job number one, just go and use what you've got better, please. With ThreadX and the SSP, it is built to support the RTOS running in supervisor mode. And that's really important because then we can put our high-level requirements, watchdogs and others in the supervisor mode and our applications in the user mode. As I say, this is not a microprocessor. This does not have a memory management unit. So these, of course, are all inside a monolithic application. So if you have a variable which isn't constrained properly, okay, well, I can use that to do some form of injection attack, and I can migrate through here. So we have to be careful in how we build these things still. The nice thing is with the secure MPU, this sits apart. You cannot do the injection attack here and force it into the secure MPU domain. So it allows us to separate our applications and critical functions so that we can then recover and manage our system a lot better. We can reset the device, we can verify the device status, we can manage downloads, and of course we can reflash the device ultimately to remove infected components. I hate to point it out, but again, this was exactly what we showed operating on the show floor the last couple of days, where we were using the secure boot to bring in key material and enable us to do a secure update on top of all of the software, firmware that was there beforehand. So, building a more secure system, security can't be an afterthought. We have to think about what we're trying to achieve beforehand. That's not to say, hey, it's Synergy, you've got some crypto, you're great. You have to understand how you want to use that, how you have to implement that. And I'm probably preaching to the choir when I talk about that. We have to right-size security. If I'm building a cheap device, my security is of necessity different from the security going into a car. That's the reality. But every device, is going to have a level of security. Every device has to be personalized, has to be managed. Cryptography is not sufficient on its own. So we talk to some of the other microcontroller vendors and they'll say, I've got a really nice, shiny crypto engine. Fantastic, that's really good. It's a nice start. But it's not enough on its own. You have to understand the life cycle of the device, the life cycle of the application that you're trying to bring through. And then we have to leverage the right tools. So Synergy has security in its DNA. It is in there, it is immutable, it is indistinguishable, it is there from the S1 to the S7. There's the implementation of the secure boot and deployment. Now, the other thing I would say is look to leverage best practice out of other groups. This is a complex science. People live their entire lives doing security. People spend years getting doctorates in security. It's complex and you're not going to learn it overnight. However, there is some help. So I'm on the executive steering committee of a new forum, the IoT Security Forum, which kind of does what it says on the tin. And the group, which is headed up by Imagination, Vodafone, British Telecom in the UK, but is going global, is all about bringing through best practices. So we know a lot of this stuff in different industries. We know in automotive how to deal with some security. We know in InfoSec how to deal with some security. We know in Mil Aerospace how to deal with some security. People have trailblazed some of these very difficult problems, and we can bring them across. The work that we've done with the secure boot is almost a copy exact of the latest security frameworks for mobile phones, because that's what myself and my colleague, who was head of security engineering at ARM for the last 5 years, That's our background. So that foundation is there. So in summary, Synergy is going to enable the next generation of security in your applications. We have some great capabilities in there. The asymmetric and symmetric crypto accelerators, that true random number generator is kind of that unsung hero. Without it, the rest of it's no good. You have to have that high level of entropy. We have the hash accelerators, we have secure storage, secure vault capability inside the device. We have to meet all of these challenges: integrity, confidentiality, and availability. And we've got to think how the attackers think. We've got to organize, we've got to think about how we'd recover from a successful attack. Is your system secure against what's coming down the lines? Put yourself in their position. Could you successfully attack your own system? And ultimately, what's the value of an attack? How much will it cost you if something goes wrong? Now, that can be liability. You know, if a big oil plant blows up, it can be a problem. I know this myself. So back in the 90s, Piper Alpha, which was a North Sea oil platform, blew up. Killed about 20 people. I was working for a company which did the actuators for the oil pipelines at the time. Now, thankfully, it wasn't our problem. Somebody had taken the big valve out and then routed the oil through an open gap. It blew up. But the cost, theoretically, of a single actuator going wrong on an oil pipeline is incredibly high. Your device may not be so critical. But if it's in medical, you know, what's your liability potentially on that if it's broken? If it's in automotive, we've seen some of the challenges there. Or it may be brand and reputation. If you're a white goods manufacturer and all of your clients' data is suddenly leaked onto the internet, or somebody takes over their heating system in the middle of winter, what cost to your brand, to your value? And that's really the only way to scale security properly. You have to understand the consequences of getting it wrong. We'll never get it right, but you have to understand the consequences of getting it wrong. Okay, so I'm slightly over time. That went very quickly. As I say, that's high level, so apologies for that. So questions? Sorry, over here first, sorry.
I'm assuming you're familiar with DPA.
Yes.
How big of a threat really is that, and what does Synergy do to fight it?
So the question was DPA, differential power analysis, how big a threat is it, and what does Synergy do there? So a couple of things. I think DPA does have some threats if systems are not created uniquely. I think there are some things which you can do around key rotation, which minimizes some of those problems. But having said that, it's down to your application as to how much you are worried about that sort of thing. In terms of Synergy, the crypto engine, which is in Synergy, was evolved from a platform which was developed for tamper-proof resistance. So I think ultimately, that's a question we'll take offline, but there is capability in there and there is knowledge of DPA and DPA countermeasures built in to the crypto engine. Next question, sorry.
Overhead.
Mm-hmm.
Obviously, the system is now built better, therefore it's built bigger, and data flows more slowly because it's being passed through these various tools. And you pay for that because you're guaranteeing a performance. What, roughly speaking, is that overhead currently?
That's a very good question. So for the camera, the question was really, what is the overhead of including all of this security in your application? It's actually relatively low for two reasons. First of all, if we do the secure boot first and we engender that integrity in the device, we only have to do that on reset. It's a relatively small amount of code. You're through that pretty quickly. And then in terms of using the crypto engines, of course, they accelerate the performance of the cryptography. So again, that's not impacting it much versus having to write it all in software. Of course, there is some overhead. There is cost in terms of engineering. There's cost in terms of performance. For a nominal application, I would say it would be practically unnoticeable once you are through the secure boot. I don't think it makes a significant difference, with the exception of saying, okay, well, if I am going to send my data securely and I need to set up the ECC or RSA tunnels, then that's going to take some performance. I think it's always worth it.
You would.
I would, yeah. Because if you get it wrong, you know, the downside of that equation is so much more massive. And I think the other thing I would say is on something like a Cortex M4 running at a couple of 100 megahertz, you've got more than enough performance there. With moving to the advanced process geometries, the amount of memory you have, the frequency, the performance that you have in these microcontrollers, it's a huge leap forward over the old ones. So I think overall, your package remains the same, the application remains the same.
I was guessing that the change of CPU, to change to Cortex architecture from the previous generation of Renesas product, has brought you these two things together. The improved architecture and the built-in crypto came together, and therefore, to some degree, you've hidden them inside the package. Is this true?
So the question again was the bringing together of the ARM CPUs and the bringing together of the crypto. Are these aligned? The crypto engine is a Renesas component which has been owned, developed, evolved inside of Renesas. Obviously, bringing forward the next generation ARM platform, the M4, has moved forward things in terms of performance, I think, quite substantially, but I'm kind of biased on that one as well. That was one of my babies. So I think in terms of absolute performance versus previous microprocessors, I would refer you back to the Renesas people in the crowd. I think they can probably answer that one better than I can. But thank you. There's another question back.
So you mentioned CAN.
Yeah.
I'm assuming you're familiar with the protocol. And so the question is, in automotive, we have a very, very small margins. And,
Mm-hmm.
as you know, the CAN protocol was never developed with security in mind. So I can have a replay attack. I can nodes don't check where the message is coming from. They just filter it based upon the message ID.
Yep.
So can you comment on how we can retrofit a protocol that can effectively and economically
Okay.
in the automotive domain?
So again, to repeat the question, with CAN fundamentally has some issues. It was never built to be secure, but there are a whole set of issues evolving in the automotive market at the moment around that, and so how do we secure those? I don't think I can stand at the front, hand on heart, and solve the entire problems for the automotive industry. I'm good, but I wouldn't say I'm that good. But I think the reality is, if you can get the integrity right in the device, then the message you can live with. And of course, in automotive, you switch the car on and off, you can manage the power. So if you can constrain the application which is on the device so that if it's attacked, it's only through that power cycle and then it's lost. If you can do the cryptographic hashes on your code package every time you start the car, then at least you can guarantee that the code that you're executing is correct. Now, and you know, in a lot of automotive applications, that's exactly what they do. There's the authenticated boot mechanisms already in there. I think we probably need to look at taking those to the next level. And also potentially having other systems which are watching what's going on the CAN bus and looking for erratic behavior. If you look at high-level gaming systems, I won't call out names, that's exactly what they do. They have an additional processor looking at the main network and looking for unusual behavior. But it's a great conversation perhaps for afterwards. Yes?
Mechanisms for tamper detection and automatic key
Okay. So the question there is mechanisms for tamper detection and automatic key destruction. So in terms of the Synergy devices at the moment, we have to be very careful about the types of threats that we're trying to deal with. Predominantly in this case, they are software-orientated attacks as opposed to a full-blown physical attack. So the view taken with Synergy as it stands today is that we're primarily protecting against software attacks. So there are some things you can do to manage tamper resistance, but that hasn't been a key goal. If that's key feedback that needs to go back into the product evolution, then that's fine. So yeah, keys normally would be kept in volatile memory, so you can get, or some keys will be kept in volatile and we can get rid of those. Inside the crypto engine, there is a component of that which can hold keys very tightly. Those keys are obviously never distributed into the system, so we can, and through key derivation, we can manage those very tightly. But it's not intended to protect against fibbing or something along those lines, so focused ion beaming of devices. Another question? Sorry, the green shirt, sorry?
This might be more of a subject for the later talk, but can you go into a little bit more how the unique identifier is created and how it's ensured to be unique across the universe?
Yeah, that's more for the later one. So with that, yes, there's a bunch of crypto behind that. Sorry. And the next question.
When you introduce all the security measures and encrypt things, it makes debugging systems very difficult, and so typically programmers probably turn all that stuff off during development. So when it goes out in production, if you want to capture traces or something and take it back to the lab for analysis, how do you go about doing that?
Okay. Yes, debug. Yes, that's the elephant in the room, isn't it? So the question is how do you enable people to develop systems with security and then switch it on and switch off the debug? So we didn't get into it so much, but again, that's for later on. The debug has a 128-bit key, so we can switch that off in the same as part of the same cryptographic schema as we use elsewhere in the system. You can develop a lot of the system without fully implementing or switching on the secure MPU and flash access windowing and those sort of capabilities. So you can develop in the open and then at the end of your process, because once you switch those on, you know, if you don't like what you've done, it's it's impossible to go back. So it's secure. So in a lot of those cases, you'll develop with those virtually in place, so you can understand the striping, but then only switch those on at the end. But at that point, yes, you would not be able to debug back inside the secure MPU or any of those controlled windows. So you do have to then branch a little bit those devices which you keep in-house where you understand what's going on, and those other devices where, you know, you fix those things, you switch off debug as you're shipping the device. There are other things which you can do. Obviously, if you're trying to do RMA out in the field, you do have to evolve capabilities for letting people have the key for that device. So there are mechanisms to extract the unique identifier. They send that to you, you send them the key, which is unique to the debug channel in that case. But that is a business capability as opposed to a technical capability. Okay. Okay, I think we're out of questions, out of time. Thank you very much for your attendance.